Hi, welcome back to the Med Device Cyber Podcast. In today's episode, we're going to go a little bit behind the scenes and talk about the 10 most common and also most dangerous cybersecurity vulnerabilities we discovered during penetration testing. And these are penetration tests against real-world medical devices. One time we found a legacy diagnostic device with a password of admin hard-coded into the firmware, and that device was in production use. So imagine the vulnerabilities with that and what somebody could do with that just by guessing the default password. I'm joined today with Myles Kellerman. He's our director of MedTech Cybersecurity. He's one of our lead penetration testers and leads our penetration testing team. And I've also got our CTO and co-host, Trevor Slattery. I think Trevor's coming from San Francisco area. Myles is coming from the same area. Both of you in the Bay Area today, and I'm in the Phoenix metropolitan area where it's like 118 degrees.
It's foggy and cold here right now, so that's crazy.
Cool. So let's cover a little bit of the background, like about penetration testing. Let's just, for those in the audience that don't really understand what penetration testing is and in the context of medical devices, let's just unpack that just a little bit so there's some context around what we're going to be discussing the rest of the podcast episode here. So Trevor, I'll throw it over to you. What's your best definition of penetration testing in terms of what we're trying to accomplish with medical devices?
Penetration testing is, in its essence, trying to simulate what a bad hacker is doing before they can do it. So if a good guy hacks into a device, they responsibly and ethically tell the manufacturer of the device how they did it so that they can go and fix these problems before it's in the market. It's going to lead to a safer product as opposed to waiting for someone with maybe more malicious intentions to find these vulnerabilities first. So it's kind of an interesting type of testing since it's practically just simulating crime to see what would happen to a system if someone wanted to really abuse it and misuse it.
So we're simulating the bad actors or the malicious software that's propagating a healthcare delivery organization network, typically.
Yeah.
And go ahead.
There are a couple of different, I think the pen testing is a little bit of an umbrella of activities looking at different goals. There are all sorts of different types of scanning, sorts of different testing. Some are automated, some are manual that go into the process, but it's pretty much just trying to dig up any flaws or poor design decisions for security that are going to introduce risk to a patient or to a healthcare delivery organization, like you said, like a hospital network or a blood delivery center, something like that.
Okay, I think one of the misconceptions, at least that I see periodically with pen testing or penetration testing, is many prospects or clients think that we are not going to find anything. Has that ever been the case? I'll defer it to you, Myles. Have you ever done a penetration test where you did not find anything that needed to be addressed from a cybersecurity perspective?
Typically not. There are a lot of variables that go into protecting a medical device, everything from the supply chain aspect all the way down to the source code. So there's always usually something there, an area of concern, or at the minimum, a security recommendation to strengthen the cybersecurity controls of that medical device. So,
yeah, and these devices are looked at through a little bit of a different lens from a risk perspective. I mean, typically in, quote, traditional cybersecurity, we look at data disclosure. So somebody steals my credit card information or my protected health information. So it's an inconvenience, but in the lens we're looking at the world through with penetration testing and vulnerabilities with medical devices, it's really about patient safety. If somebody hacks into the defibrillator and shocks you to death, it's a little bit more severe than your credit card information being stolen. You can recover from your credit card information being stolen, but you can't recover if you die from being shocked to death, obviously. So the risk is much greater.
Getting shocked to death is pretty permanent. And when we're going through the risk assessment process, it's very different from that regard. We have to look at how we're blending security and safety, which is completely unique to this industry. And so in security, they talk about the CIA triad: confidentiality, integrity, availability. that's going to be relevant in the medical space, but we add the new CIAH quad square. And that H would be for harm. So looking at, can we harm an individual? Can we cause direct pain or discomfort to a patient? Can we delay treatment, misdiagnose a disease, something like that? There is a lot that can go wrong with, like you said, Christian, lasting permanent damage in many cases.
Yeah, and I think about this in real world examples. Like my grandmother passed away, but before she passed away, she was hooked up to a drug infusion pump. And as a lot of people are in the hospital, and there have been many vulnerabilities with that particular model. And if something like malware was propagating that hospital network and happened to hit that drug infusion pump and increase the flow rate of a drug she was on, let's say morphine, then she could OD on morphine and actually die, sooner than, she did. So, the risk is pretty great. Hits pretty close at home as well. So let's jump into the top 10 here, the top 10 common vulnerabilities we find. Number one I have on the list here is hard-coded or default credentials. And I mentioned a little bit about finding the firmware with the password of admin so we could get into the device firmware at that level. From your experience, Myles, do we find this pretty often? And what's a couple of the more common findings, either on the device itself, the mobile app or the web app? Because typically a medical device has all three of those components. Sometimes it doesn't. But what's your thoughts on this particular vulnerability?
Sure. We see this far too often, whether it's coming downstream from the supplier, having default credentials set that are never noticed by the receiving client who's trying to put this device out to market, or just totally not setting additional security configurations to enforce not having a default password. So we've seen many examples of this. A lot of times where I see it is in during static code analysis. We will see these passwords hard coded in, and then with device access as well, when we're physically testing medical devices, we'll find that certain menus are using default passwords that can clearly be looked up on the internet, or just best guess passwords, either using like the company name or just as simple as admin or password 123. And to kind of follow up with that too, one of the major findings for physical devices is, or I should say probably with any medical device that's using a computer of some kind, is going to come down to like the BIOS password. That leads to a lot of nasty things that can happen down the attack chain if leaving the BIOS password not enabled. So there's a lot of that would probably be the most impactful. Besides the hard-coded password, would be BIOS passwords not enabled.
That's hard-coded to nothing. Or not enabled. No, that's a good addition there, because it's not just hard-coded passwords that are easy to guess or are documented somewhere or in the source code. It's sometimes there's not even a password set for like the BIOS, as example, like you mentioned. And something as you're talking came up because a lot of medical device manufacturers outsource their software development, and you're talking about supply chain, Myles. So I think this is a critical point, because if I've outsourced my software development and I'm a MedTech innovator, I'm assuming the company I've outsourced the development to knows how to do secure software development. But from our experience, that's extremely rare. What do you think about that, Trevor?
It's far too common that we see engineers just developing medical software the way they would develop any other software. And there are a few things that can go wrong with this. We've already talked about the fact that medical systems have higher risk than other systems just because we're dealing with patient safety. But moving through regulated industries is much harder than, say, I know in the past we've talked about the Silicon Valley mindset, move fast and break things. I can look out the window and I see all the signs on the bus stop advertising some weird new AI tool that someone created 3 weeks ago. And that's great for a lot of industries to just try to make code, get a product out there. But in a regulated industry such as healthcare, There are processes that need to be followed, standards you need to adhere to, documentation requirements, and traceability that is just far too commonly missing.
So you're suggesting or inferring that a software development company in medical device should be following IEC 62304, which advocates for secure software development for medical devices.
Definitely. And then there's IEC 81001-5-1, which talks a little bit more about that total product lifecycle and that secure software development. And so both of those standards in combination are great for medical device manufacturers to look at. So if like an OEM is trying to hire in-house talent for this development, they should look to developers who understand these standards. Or if they're trying to outsource their contracting to a third-party shop, they want to make sure that that development team understands these standards. They're creating documentation that lines up with ISO 13485, so there aren't going to be any roadblocks down the line. It's also just assumed that they're going to create more quality code. There's going to be more security baked into their code. They're not going to introduce as much unnecessary risk.
Yeah, so we're advocating with medical devices, it's a regulated industry, so the software development firm should follow IEC 62304 versus, it's ironic both of you are in the Silicon Valley, which you make it sound like there's bumper stickers all over that say move fast and break things. Have you seen those all over the place?
Can't say I've seen those. I did learn a crazy fact, though. In San Francisco, there is a startup for every 20 people in the city.
That was probably somebody's startup that came up with those statistics.
Probably. But just goes to show people do like to just try to make something.
Cool. Well, I guess the follow-up statistic would be how many of those startups actually succeed, right?
I would say less than 1 in 20.
And what defines a startup? A lot of people have an idea. If I have an idea and I tell 2 people, does that mean I have a startup or do I have to form a corporation? That's a different topic. So let's go to number 2 on the top 10 vulnerabilities in medical devices, which is unsecured communication channels. And this could be unsecured in a number of methods. How do we see this in medical devices typically? I'll throw it to either one of you that want to answer.
Yeah. So with this particular topic here, we find this a lot. It can come in many different forms, whatever interface you're testing, whether it's Bluetooth, Ethernet, and even wireless. We're trying to look at data flows that are encrypted. So encryption in transit to protect the patient data if there is any part of that data flow. And so some of the things we see are no encryption at all for the data in transit. And that includes PHI or PAI being part of those data flows, to maybe they're using encryption, but it's maybe a standard that's no longer supported or has been sunsetted. So an example of that would be something we see all the time is your encryption and cipher suite, such as TLS 1.0. We really don't see too much of any of the other weaker encryptions, but those configurations need to be made to make sure that stronger cipher suites are being used if encryption is turned on for those data flows. But that's typically what we see out of these devices. Yeah.
Yeah, I know one thing that I've noticed in a couple of devices that we've worked on, it wasn't just the type of encryption, it's how they did key management. It was very easy to figure out what the key was. So it doesn't matter how great the encryption is. If you don't protect the keys that are used to encrypt the data, then you can just decrypt the data, even it's, TLS 1.3. It doesn't matter.
There's a great standard that the FDA calls out, FIPS 140-3, which talks about latest and greatest encryption standards. And they're in the process of trying to sunset FIPS 140-2. But this talks about when you can use certain levels of encryption, what those encryption standards are. This does need to be a little bit of a risk-based approach. If you're just transferring harmless machine data or like startup logs, just diagnostic information relating to the device, nothing sensitive relating to patient safety, nothing that can be used to compromise the system further, encryption on that information is going to be less important as opposed to transmitting PHI, transmitting diagnosis results, things of that nature.
Yeah, and that brought up a question in my mind, or something, a topic here. We work with a lot of implantables which have, they're battery powered. And if we add all this encryption, which may not be necessary for what the data you're talking about, which is diagnostic data, then we're draining the battery life of that device much quicker, because encryption takes a lot more processing power, which therefore drains the battery. So how do manufacturers find that balance?
Well, we can use that implantable device example. If you have an implantable device and there's no way to access what information is inside of it without removing the implantable, what is really the risk of someone doing that? Why would you need to encrypt the data at rest in the system? So just understanding where there's that balance. Security has to be a balance. There's functionality and security often clash directly. We always talk about perfect security is nearly impossible. You can't really have any connections. You can't hardly have any code. And so it's just going to remove any usefulness of the product. When we have situations like that, where we're very resource constrained, it should come down to what can be accessed and what can't. And if there's something that's inaccessible, we can have some looser controls around it.
Awesome. Let's move to number 3. 3 is on my list here, is outdated or vulnerable third-party components. And this is where the software bill of materials, or the SBOM, comes into play. And I think there's been a big push for this for a long time, since Heartbleed came out, and even Shell Shock back in the day, because a lot of HDOs didn't know the device, and even medical device manufacturers didn't know that this medical device even had these vulnerabilities, because they did not understand the third-party components that made up that device. So can we talk about, do we see this quite often, like outdated and vulnerable third-party components, when we do our SBOM analysis?
Yes, absolutely. They're the only clients that we see very few findings for. We'll just take the SBOM part, are clients that are already running tools for their SBOM to, track and mitigate the threats that come through with those third-party components. Outside of that, we're finding vulnerable components in CMD products or web applications and mobile devices as well. So it's I don't want to say it's kind of whack-a-mole, because it kind of is, because new vulnerabilities come out for these third-party components constantly. So, but it's a necessity to make sure that these things are constantly tracked throughout the product's life cycle in order to maintain good cybersecurity hygiene.
Yeah, and that's a very good point, because there's a lot of emphasis with manufacturers on getting the product to market. So they do the SBOM analysis. It's all, the vulnerabilities are mitigated. It's good to go, and it's on the market. But then a new vulnerability could be discovered, one of those third-party components, after it's on the market or cleared to be on the market. So that's where that continuous monitoring comes into play, as you mentioned, Myles, that post-market management. Cool. We'll go to number 4 here. Number 4 is improper access control. I'll throw it over to you, Trevor. How often do we see this with medical devices? And this could be logical or physical, I guess. It could be either one.
This one is super common. I'll talk to the logical one first. So when we're looking at access control, that's the FDA terminology would be authentication. So how are we determining who is authenticated into different levels of permission, different amounts of information, different levels of access? For an example, if we're looking at our email accounts, I shouldn't be able to read Myles's email, and Myles shouldn't be able to read my email. But the IT admin for, who's handling Gmail can handle all of our emails in our organization. So they have different levels of permission, and it should be gated appropriately. We see this all too often, where one user is able to read another user's information. This can be very dangerous, especially if they have PHI involved, or one user can, say, like a general user can access an admin role. Things of that nature are very common in software as a medical device, and I would say it's one of our more common findings on pen test reports.
Cool. And what about you, Myles? I know you've had pretty good success with breaking into web applications that are part of a medical device because of the improper access control.
Absolutely. So there are many instances that I could go over, but it's paramount that if there's multiple users, let's say in a web application, that the medical device company needs to make sure they're testing the difference between what the admin or high privileged user can access versus what the low privileged user can access, and really do, it comes down to doing the pen test to figure out what that low privilege user can and cannot do. A lot of times I'll find that the low privilege user can use an admin function that it's not intended to be able to use or even see. And then that goes into like information disclosure of patient data even. So it can really get nasty with not having a proper pen test that checks the access controls. One thing to note on that, even we have findings to simplify it down, for replaying a web call that accesses data. We've seen it as bad as deleting the authentication mechanism out of the request, such as a cookie, and at the simplest form, a cookie, and replaying that and still getting data back. So just being totally unsecured or not even using authentication to even, see that valuable data.
Yeah. Awesome. So let's move on to number 5 here, which is debug interfaces left enabled. And there's 2 primary debug interfaces with medical devices. There's UART, which is, we don't see that too often, but there's also JTAG. From our experience, I'll throw this over to you, Trevor. How often do we see this, or is this really a problem, or like are most manufacturers pretty good at mitigating this one?
This one is a little bit of a unique problem since it's very easy to mark these ports as out of scope of testing. So JTAG and UART will be a little bit different from, say, a USB port, which is intended to be exposed on the outside. But if we have a JTAG port, UART port, usually that's going to be on a printed circuit board itself. So that's deeper in the system. If you need to shred apart the plastic on a device, tear it open to access that port, that's going to be evidence enough of compromise. Another thing with these attacks is the attacks are usually generally quite complicated once you do have that level of access. But if they're successful, they can be devastating. You can entirely rewrite the functionality of the device to do whatever you want. You can siphon out any information that the device is capturing to your own controlled endpoint. You could change the way that therapy works. You can remove any safety controls and restrictions. It's essentially the keys to the kingdom if this is successful. Having said that, generally, the control is to make it inaccessible altogether. The only way is to flash on the firmware during development and then bury it far enough in the device where nobody can touch it.
So once the device is done being developed and is being pushed to production, wouldn't another control just be to disable these debug interfaces? Because what's the point of using, why do they still need to be enabled if the device is in production?
They can be used for maintenance, so updating the device or, any diagnostic as needed. Generally, the control would be you can lock one of these ports, so you'll need essentially authentication to access anything on the inside, which is going to be an added layer of control. This allows for manufacturers, say a device is not operating properly or they need to do an update and they don't have over-the-air updates enabled. They can take the device back, flash on new firmware, change the functionality without exposing it to the outside. So that JTAG authentication, UART authentication is going to be a great compensating control while still keeping that functionality in place.
Okay. It sounds like that's the authentication is a control as well as perhaps having tamper-proof seals that would have to be broken in order to get into the device to get to the UART or JTAG port.
Exactly. Yes.
Cool. We'll move on to number 6. I know we've had this with a couple of our clients. Missing or weak firmware integrity checks. I know the FDA is an advocate for secure boot and code signing. Those are requirements. So have we seen this quite often, and what can manufacturers do to help mitigate this?
This one's a little bit unique and that it's generally generally harder to see from a pen testing perspective, unless you're going into that white box level of access, which is our preferred approach to ensure complete coverage. So I guess I'll step back a little bit and talk about the different perspectives of pen testing. Black box is without information. That's generally from the angle of like an unauthenticated outside actor. Gray box is some information. Maybe you have a password, maybe a little bit of information about components in the device. And then white box is full access. You have source code, documentation, everything that's going on. This is usually the step where we're finding out that there aren't firmware checks. There's no secure boot. There's no code signing. They don't have any CRCs looking for software or firmware integrity. And it can be a real problem. It'll go back to those debug interfaces. If someone can flash on their own firmware or modify the existing firmware, it can be extremely dangerous because they can change it to do pretty much anything they want.
And this is why we do white box penetration testing, to cover these things, which would reveal even the type of microcontroller and chipset that a manufacturer has chosen, because certain microcontrollers don't support secure boot. So we have to look at it at that level as well. Let's go to number 7, which is poor session management. And one of the items of this is like a session token that doesn't expire. You mentioned cookies earlier, Myles. Maybe you can explain what a cookie is and a little bit about poor session management and how that can be abused.
Yeah, so at a high level, cookies are part of the authentication mechanism for any web app, or we'll just say any web app or SAMD product using a web interface, right? To secure the product. So to get to the session management piece, this can come in many forms. So poor session management, the top form that I see a lot would be if the session does not have a timeout period. So for example, if I log in, a session's created for me while I'm logged in, and then what happens next is I hit the log off button. And then when I hit the log off button, better security would be to have that session invalidated as soon as I hit the log off button. What we see with a lot of the products that are designed is that either it's maybe has a little bit of slack in the time between the log off button and let's say like 10 seconds before the session's actually invalidated, or there's no invalidation at all. So what that means is if an attacker can compromise your session somehow through the means of social engineering or some other attack vector, they can reuse your session for as long as they want to do what they will with it. So with that being said, typically what I'll do is I already kind of described part of the attack, but I'll log in, I'll get a usable session that looks at data and as a request, and then I'll hit the log off button, and then I'll replay that particular session or make that request again with that session token. And if I can view the data or get a response, a 200 OK response or whatnot to see the data, then that session, is vulnerable. Another thing that we see is like security controls wrapped around session management. So great design for a web app product would be to when the user logs in and obviously they created a session, they can go, let's say, to their profile and they can see that they're logged in from their laptop and like their IP and just kind of like a logging mechanism to tell the user that they're logged in from a particular like region that they live in. This is good. So if sessions are allowed on two different public IPs, that means obviously that a bad guy can log in with the same session you have from a different region or different location. Having that logging in your profile to say, oh, well, there's another session from this other, or there's the same session, but from another public IP, this would tip the user off that somebody has stolen their session and, obviously is using it somewhere else. So just session management is made up of multiple things or multiple controls to make sure that, we're preventing bad actors from using stolen sessions and taking advantage of no session timeouts and things like that.
Yeah, you brought up a great point there. And I just want to summarize what you said. It sounds like a lot of device manufacturers, when you click on the logout button, it makes it look like it logs you out, but it doesn't actually invalidate the session. That was one of the points you brought up. The second one, which I think is important from a user perspective, if I can see, if I'm always in Phoenix, for instance, but I see a session from Azerbaijan, then I'm like, well, that's not me. I'm obviously not there. So I know that something is going on. So it's another control that should be put in place also. That's a good point. So it brings us to number 8, which is fuzzing. And we need to kind of describe what fuzzing is a little bit. But fuzzing is something we do as part of our penetration testing, but it often reveals what we call buffer overflow or a denial of service. So I'll throw this one to you, Trevor. Maybe you can just give a brief definition of fuzzing and what a buffer overflow is, because that's often why you do fuzzing, to find a buffer overflow.
Sure. So fuzzing is pretty much just taking tons of different bits of input and putting it at a certain field or connection that is meant to receive input. So you might see, say, a password page, and you say, what happens if the password is 1 character long, or 1 character long, then 2, then 3, and you go all the way up until you hit 100,000 characters long, just to see how it responds. And oftentimes there will be a problem where the system does not handle it properly on the back end, and this can lead to, most commonly, a denial of service, which is when the system can no longer operate due to receiving unexpected input that causes it to crash. And this is often through a buffer overflow. Now, a buffer overflow is going to be constrained to certain use cases. Generally, this is with older systems, or they call it memory unsafe languages. And so what we're really trying to do is overwrite the computer's memory into space that shouldn't be captured by the application. And so it's going over what is allowed and then just spilling out into the computer. And what can be really dangerous about that is that overflow, the part that spills out into the computer, you can redirect it into other parts. And so that can often give you control and access to sensitive functionality in the system. You can either redirect it to another part of the medical use case, or you can access just certain computer functionality as a general. It's a pretty complicated attack, and I will say it's becoming less and less common as more memory safety protections are put in place on computers. Coding languages are increasingly less vulnerable to it. Modern languages, such as C#, Rust, and then most web languages are not vulnerable to buffer overflows. It's when we're looking at C, C++, some of these older languages that are very prone to problems here.
Yeah, and we still deal with a lot of older medical devices, the legacy devices that are vulnerable to buffer overflows. I remember back in the day when I used to do hacking myself, hands on keyboard, I was pretty good at buffer overflows, because the whole idea is to inject enough buffer and then inject your malicious code and trick the system into running your code. So instead of running what it's supposed to be running, the system runs your code, and that therefore it can obviously be very malicious. Plus there's also the denial of service aspect. And if we're dealing with a medical device that is a critical system that needs to return a result in a couple minutes, of course, the denial of service is a big problem. So let's go on to number 9, which is tamper detection. So how do we know if the device has been tampered with? And there's 2 aspects of this. There's a physical aspect and a logical aspect.
There are a couple of ways that we can have tamper protections. The first is just a clean audit trail in the device. Anytime something happens, we want to have a record of it in the form of a device log. Someone logged into it, someone changed this configuration, someone accessed this database. This is how they accessed this database. This is what they changed in the database. These are the things we want to see captured that'll prove if someone got in and changed something they shouldn't have. that would be more on the, I guess, software side or the logical side. But on the physical side, we can go back and look at these problems we talked about with debug ports like JTAG, UART. If we look at a device where you're able to just pop it apart, it has, maybe one or two screws and the whole thing falls apart and you can put it back together without anyone noticing, that wouldn't be a great control. But we often recommend that you can put like tamper evident stickers that need to be signed by a service technician over these panels. So if the panel is open, that sticker would need to be torn or cut. And then you have a labeling control saying, hey, before using the device, check these stickers, make sure they're intact. And if you see that one is broken, you assume the device has been compromised and tampered with, and you shouldn't use it. So that would be from the more physical side of things.
Awesome. And let's move on to number 10, which is no rate limiting or automation controls. And rate limiting, it means we're limiting the number of actions that can happen or requests that can happen in a specific time frame. All right, Trevor, do you have another example for rate limiting? What are some examples that you've experienced?
We've had rate limiting is a pretty common finding. Brute forcing attacks are a low-hanging fruit for a lot of hackers. And brute forcing is trying to just use a ton of different passwords against a single login, or a single password against a whole bunch of logins, and trying to see if they can get a match. Oftentimes what we'll see is that you can have a list of common passwords. There are tons of lists online where it'll be, the top 10,000 most commonly used passwords, or 100,000 or million or whatever it is. And if you see that there's rate limiting in control, it'll be the same as when you try to go and you put in your phone password wrong 4 times. It says you have to cool down for 30 seconds before you can try again. That would be a good example of proper rate limiting. But if we see that we can try our phone password 10,000 times and nothing happens, then we can set up an automation, which is what we're doing in these cases, which does these 10,000 attempts in a matter of seconds. So we're able to quickly guess millions of passwords against a single email or login, and it's pretty successful. People aren't the best at having good passwords in on their devices, and so we're trying to abuse that fact by abusing a device control that is not in place.
Yeah, awesome. We're coming up on time here, and we hit the top 10. I think we gave a pretty good, decent example for each of them. And I just want to reiterate that all the top 10 we talked about, each of the individual ones, that we've given you real examples. It's not theoretical. And one of the ways to prevent some of this, penetration testing is kind of reactive. But from a proactive perspective, if you do what's called a secure product development framework, or you have DevSecOps, you do secure software development and have a pipeline in place with certain security checks as you're developing the code, that can help prevent a lot of these vulnerabilities. As I mentioned, penetration testing is more reactive. And unfortunately, when we're called in to do penetration testing, we find a lot of vulnerabilities that often result in a lot of extra effort on the manufacturer to fix them, versus if they would have enabled a secure product development framework early on. And one of the things to consider, and there's a big push towards this, is the FDA and other regulatory authorities, they don't want your device to be safe most of the time. They want it to be safe all of the time, because the risk is super high. As we talked about, we're dealing with patient safety.
You say the surgical robot works most of the time. We're good at transplants most of the time. Don't worry about the rest of the time, though. Now, it has to be, the risk is so high, so the security controls have to be just as high to compensate. There's very little room for error in a lot of these medical devices, and we need to make sure that that's considered when we're handling security there.
So thanks, everyone, for tuning in to the Med Device Cyber Podcast. I hope you found this episode on the top 10 vulnerabilities we discover in medical device beneficial. If you ever need a medical device penetration test, please feel free to reach out to Blue Goat Cyber. That's what we specialize in, along with full service submissions. Thanks, and have a great one.